Okay, so last time we had introduced the real projective plane for the first time. So to just remind you of, so we did this to give ourselves, a model for our projective plane, right? So we started out with our projective plane um, axioms, and this definition of RP2 showed that they RP2 actually satisfied those projective plane axioms. So we'll see a little bit later that RP2 is not the only projective plane. So there are other projective planes, and RP2 differs from some of the projective planes in a way that can't be as a result of the axioms, because when we say something's a projective plane, we mean that it satisfies those projective plane axioms. And so if there's any differences between RP2 and those other projective planes, then it has to be coming from something that's not derivable from the axioms, right? Okay. And so RP2 was a set where our points in RP2 are lines through the origin in R3, that is, lines through the origin in space. Lines in RP2 are planes through the origin in R3. Okay, and the plane that we talk about is the set of all lines through the origin. So it's the set of all the points, right? Okay. And then we get that it satisfies immediately, just from what we know about geometry in R3. It satisfies those three projective plane axioms. And so this seems weird intuitively when you think about it, because our points are actually lines and our lines are actually planes. But our reason for this then is that if you, and I showed this image last time, like what is the relationship between this and perspective? We'll see one angle of that in a little bit when we talk about where this geometry gets its name from. So where the word projective comes from. But what's the relationship between like RP2 and the things we were talking about before with perspective? So the idea is that actually this is related to seeing with an all-seeing eye. And the way that it's related to that is now imagine that I have the following picture. So here I am in space. There's my X, Y, and Z axes. Imagine my all-seeing eye is at the origin. Okay. So then how do points in, say, Euclidean space, right, get matched up with lines that go through the origin? So my all-seeing eye is at the origin, and if I draw the lines connecting my all-seeing eye to points in the plane, then what I get are lines, right? So I get lines associated to points. And so what I have then is, well, instead of a point, P1, I have the line that connects my vision to that point, right, from the place I'm looking at it from. So here, the origin. Okay, and so I get lines through the origin corresponding to points. Okay. So then what's another example of what I get here? Well, another example of what I get is, note that if these points tend off, so this plane is just a plane z equals -1. So as that thing goes off indefinitely, and so let's say I have points P1, P2, P3 going off along this line M, off to infinity toward the edges of the plane, what happens to my vision lines? As I draw those vision lines further and further out, those vision lines become horizontal, right? Or they tend toward being horizontal. Okay. So they tend toward being horizontal. And so, for instance, for this plane, that horizontal line that they tend toward is my point at infinity, okay, for this plane. All right, since it is a line, right, that would be horizontal, it's the point at infinity for this plane. Okay, but imagine me doing this for several planes, right? And imagine me doing this for several different points, not just one associated to this line M, right? Then what do I get? I get a collection get a collection of horizontal lines, right, through the origin, right? So I get a collection of lines lying in the, say, xy plane passing through the origin. Okay, well, in that case, this would be the line at infinity, right? This would be the horizon for this plane. The collection of all those horizontal lines would be the horizon or the line at infinity for this plane. Okay, so that's how we can think of a plane passing through the origin. That's one example, is the collection of all the points at infinity for various lines in this plane. And so what this means is that, say my plane, say the xy plane passing through, the horizontal plane that passes through the origin, here is my horizon line, right? Since a line in RP2 is a plane through the origin. Okay. Now, so in this way, this notion of associating to points in Euclidean space some other object, so in this case lines, that means that the points and lines match up. So points in Euclidean space match up to these lines in Euclidean space that we're calling points in RP2. Okay, and so what is the analog for these lines at infinity? Well, they don't really have an analog. So as we'll see, these lines at infinity, or points at infinity, extend the Euclidean plane. Okay, in our example, our Euclidean plane is modeled by the plane z equals -1. Okay, so one of the things that we said was that there's nothing special about the plane as we describe it. It could be any plane in space could be our model for the Euclidean plane. Okay, it doesn't need to be horizontal, doesn't need to be oriented in any specific way. Any plane in space could be a model for the Euclidean plane, right? That was part of the strength of all this linear algebra stuff that we did in the last chapter. Okay, all right. And so these extend the Euclidean plane, but we'll see exactly how later. Okay. So if any of you have had topology, or maybe you've seen this somewhere else, there's a thing that I'm going to do right now that will make it clear where this is headed. But I want to do this now anyway because we're going to talk about this later. So to see how this works for a projective line. So what do we mean when we say projective line rather than projective plane is what we mean. So to see how this works for a projective line, we want to ask ourselves the question. So the reason why we want to do this is it's hard to find or describe a surface that behaves like RP2 does. Okay, but, another parenthetical statement, but it is easy to find a curve that behaves like a projective line. So later we're going to have a model for this projective line, and it's going to be called, unsurprisingly, RP1. Okay. But we haven't defined this thing yet, so we're not going to define it immediately like this right now. So then what is our way of describing a projective line? So basically, the idea is that I have my origin O. Okay, so I have my origin O. And maybe I should have used my, here, let's just coming up with reasons to use my compass again to make the picture look nice. But I don't want it to actually be centered at O. I want O to be one of the points. Oh, well, that defeated the purpose. Here, I'm just going to freehand it so that, as the compass was a cheap compass and it's already given out. So consider the circle with O on the circle here at the North Pole. Then what is the idea to associate points on this circle with lines? Right, so how do I associate points on this circle with lines through the origin? Well, there's a straightforward way. So for instance, this point, P1, is associated to the line passing through the origin and that point. So it is that line, right? And some other point, P2, is a point, and the line associated with it through O is just the point passing through O and P2, right? So the same thing is true over here. If here's P3, then the line through O associated to it is exactly the one you expect, right? Okay. But what about O itself? O itself is a point in the circle. Which line through O is it associated with? Well, the tangent line. Right. Okay. All right, so that point corresponds to the tangent line. So what we're doing here, i.e., we have modeled in the same way a projective line by a circle. Okay, we've modeled a projective line by a circle. Okay. And as we'll see in a little bit, probably not today, probably next time, this RP1 can be thought of as just an alternative definition of a circle in some way. Okay. And so we'll see exactly how that works once we bring it up. The idea here is that what would RP1 consist of? It would be a line consisting of a bunch of points, those points corresponding to lines in the same way that the points of RP2 were lines through the origin. So here, our points on this circle correspond to lines through the origin O. Okay. All right. So one more thing about points at infinity in RP2. All right, so one more thing. About points at infinity in RP2. So basically, each line only has one point at infinity. Okay, why? This is an important thing. y. Going back to our picture again. So look at the line M here and points, right, as these points P1, P2, P3 go along M out, right? Thinking about the vision line, right, that I would get if I kept drawing in these points as they went on and on further and further out the plane. Well, as those points tended off, the lines that I get, right, connecting my origin to those points, that line is going to be the same horizontal line. It doesn't matter whether P is tending to infinity along the line in this direction, whether the P's tend to infinity along the line in this direction. The horizontal line that these vision lines converge in some sense to is the same horizontal line, i.e. it's the same point at infinity, right? So the same, the lines, say L1, L2, L3, and so on, tend toward the same horizontal line. Okay. Thus, the line M, oh, that's not an M, that's something else. Thus, the line M has one point at infinity. Right. It's the parallel to M through O. Okay. Okay. All right. So that's the last thing I wanted to say about this. It makes the notion of these points at infinity a little bit more intuitively clear what's going on and why they would be unique for a line. Okay. This brings us to ways of describing our space RP2. So this is done via homogeneous coordinates. So what's the idea here? Okay, note points and lines of RP2 are lines and planes through the origin in R3, right? Thus, they're describable by equations that we talked about previously, right? So they're describable about the equations we talked about in the last chapter. And thus, they are easily handled by methods of linear algebra. Okay. So think chapter 4 stuff. Okay. So note any line through the origin O is determined by a point that is not the origin. So it's determined by a point, xyz, that's not the origin, and thus, using our linear algebra, you can think about this as vector algebra stuff. What does this mean? Well, the vector associated to this, of course, is the vector that is associated to this triple, but of course the line, right, determined by that vector would be the set of all scalar multiples of this thing. And so thus any point, or thus it consists of all multiples, or all points, say tx, ty, and tz, where t is any real number. So every point along that line is tx, ty, tz once you have a point on the line that's not the origin for some real number t. Okay. So thus, a point in RP2 is not given by a single triple, but by any of its non-zero multiples. All right. So once you have any non-zero multiple, right, then you have a complete description of the line through O, and thus the point in RP2. Okay, so these non-zero multiples, these triples, are called the homogeneous coordinates of the point. These are called the homogeneous coordinates. So in this textbook, he doesn't use a special notation for when he's talking about homogeneous coordinates. Sometimes you'll see, if you look this up, you'll see brackets, square brackets used like this. More generally, the way that it's used is x naught, x1, x2. The fact that it counts it as x naught is meant to be the n that it goes to here is supposed to match the same number that I've written as my dimension here, right? It's a real projective plane, right? So it's two-dimensional in some sense, even though we know that it's defined by objects sitting in R3. This is still a two-dimensional object in some sense. That's why this notation is not totally crazy. And so that's why this numbering begins at 0 typically when it comes to homogeneous coordinates for projective space, is so that our top subscript matches the number of the dimension. Okay. All right, so sometimes, like I said, you'll see this notation, although I'm not really going to use that here. But this is, when you see this, what this means is that this is only defined up to scalar multiplication. Right, you're allowed to scale this any way you want to, and it's the same object. Okay. All right. So note a plane. So recall a plane through the origin in R3 has a linear equation of the form ax plus by plus cz is equal to 0. Okay, and this is called a homogeneous equation. Okay. So the same plane is also given by the equation. So the same plane is also given by the equation tax plus tby plus tcz equals 0 for any real t not equal to 0, right? And so I also have homogeneous coordinates describing planes in the origin through the origin in R3. Okay. Thus, similarly, a line is not given by a single triple, ABC, but rather any TA, TB, TC, right, for non-zero T. Okay. Then, how might we use this to our advantage to work through some of the things that are kind of like intuitively needed, or what we expect to be satisfied here. So note, if, say, x1, y1, z1, z1 and x2, y2, z2 lie on different lines, through the origin, then they lie in a unique plane through the origin. So they lie on a unique plane, say ax plus by plus cz is equal to 0. Right? To find this, so the coordinates ABC of this plane can be found by solving the two equations simultaneously. Ax1 plus by1 plus c z1 is equal to 0, and ax2 plus by2 plus c z2 is equal to 0. Okay, by solving these for a, b, and c. All right, there's more unknowns than equations, so that means there's not going to be a single solution triple. There's going to be a whole space of them. That's going to be all the multiples, right? So more unknowns than equations. So we get all multiples. TA, TB, and TC. Okay. All right. So this type of reasoning is exactly the same reason why 2 points lie on a unique line, and there's a similar reason why 2 lines have a unique point in common. Right? So what does this say? Well, this is algebraically why 2 points lie on a unique line, right, in RP2. Similarly, 2 lines have a unique point in common. Okay. Recall 2 lines have equations a1 x plus a2 y plus a3 z. Sorry, I shouldn't label it like this. Let's do a1 b1 c1. That's better, is equal to 0, and a2x plus b2y plus c2z is equal to 0. There. Okay. So 2 lines have these 2 equations, and we can find their common point by solving for x, y, z, right? So solving for x, y, z finds their common point. Again, there's more variables than equations here. We're going to get all the multiples here as well. So in homogeneous coordinates, we still get 1 point. Okay, so those are the homogeneous coordinates. There's some exercises that I'll maybe assign later after your exam where you go through and do some of this. But this is it's pretty straightforward. This is just reassuring you that the stuff works out the way that you think it should. Okay. The main thing that should be mentioned here is note algebraically I could have done all this for complex numbers just as well. Right? It makes no difference if the coordinates for lines and planes are complex numbers. Okay. This leads us to CP2, the complex projective plane. Okay. So what is the deal with the complex projective plane? Well, the complex projective plane is just going to be the set of triples, right? So what is this? The set triples tx, ty, tz for x, y, z complex numbers. Okay. And t running through all complex numbers. Okay. All these things we said previously remain true. So it remains true that any 2 points lie on a unique line, and any 2 lines have a unique common point. Just because these algebraic properties we went through are exactly the same, whether or not I'm dealing with complex numbers here or not. Okay. We can also show that there are 4 points, no 3 of which are in a line of CP2. And so this is another example. So this is another model of the projective plane. Okay. And as we'll see, it is different than RP2. Okay, but it satisfies the projective plane axiom. So as a model for the projective plane, it at least satisfies those. Okay. So there's more than one model of the projective plane axioms. Okay. All right, we're going to see more than this too. So these aren't the only 2. There's more models than this, and we're going to see exactly what properties of RP2 come from the projective plane axioms and which ones don't. Okay. So right now, this is only our second model for the projective plane. Okay. Now, moving kind of similarly in that direction, not sticking to planes, but I mentioned this before. What about RP3? Right? What about RP3? So using this, now I kind of have the algebra backing, right? I've gone through why these things work. What about RP3? Can I define a real projective space? Okay. The idea is to generalize to homogeneous quadruples. So I would have quadruples x, y, z, w. and thus define RP3 similarly as real projective space, right, in the following way. So algebraically, I could say, well, this is the collection of homogeneous quadruples here, right? But what is the geometric idea? What's the thing that allows me to say all this? Or, you know, what is the thing that I can do here? I mentioned this when we first defined RP2. So a point in RP3 is a line through the origin in R4, right? Which is why we need quadruples here. That is, i.e., a set of quadruples TU, where U, this vector U, is determined by you know, X, Y, Z, W. Right. I think the book reverses these. It puts W first. That's perfectly fine. And so T is, you know, running through all the reals here. Okay. So then what would a line be? So a line is a plane through the origin in O4, or sorry, through O in R4. So, i.e., set T1 U1 plus T2 U2, where U1 and U2 are linearly independent. This just ensures that we have general position, right? If the two vectors aren't linearly independent, if they line up, then this doesn't determine a plane, it just determines another line. So, so anyway, so we want these to be linearly independent so that they actually determine a plane here, or some object big enough in dimension. So, you know, where these are linearly independent in R4, and T1, T2 run through all the real numbers, right? So T1, T2 are reals. Okay, and then what is a plane here? So a plane in our three-dimensional space is in our four-dimensional, it's in R4, is where the object sits, but our RP3 is supposed to be a space. It's modeling projective space here. So a plane in RP3 is a three-dimensional space through the origin in R4. So what is this? This is i.e. a set T1 U1 plus T2 U2 plus T3 U3, where U1, U2, and U3 are linearly independent, and T1, T2, T3 run through all the reals. Okay. All right. Then we can use linear algebra, like in the last chapter, and show a bunch of facts geometrically about this real projective space. So these are the properties it satisfies. This isn't like an exhaustive list, but it is a curated list for a specific reason. So two points lie on a unique line. 3 points not on a line lie on a unique plane. I should say determine a unique plane. 2 planes have a unique line in common. Note how this is different from Euclidean space, where in Euclidean space you can have parallel planes. Here all planes meet, just like how all lines met in the projective plane. And 3 planes with no common line have one common point. So 3 planes with no common line have one common point. Okay. Okay. So these are our axioms. These are the things that hold for any three-dimensional projective space. So these all hold for any three-dimensional projective space. Just like we defined the projective plane axioms. Okay, thus, RP3 is a model for such a space. Okay, but as before, not the only one. Not the only one, because CP3 is another model. Algebraically for the exact same reasons. Okay. Now we won't return to discussions of RP3 until the end of the course, or near the end of the course. But RP3, all of these spaces we're talking about have huge ramifications for what we'll discuss later. So this is not just a one-off thing we're going to define and then move on and not talk about again. This is going to be something we return to over and over and over again. Okay. All right. So, these, before maybe it seems like we've gone too far away from our original concern with perspective drawing. That is where this stuff came from. The question is, why is it called projective geometry? Okay. So it turns out that our mathematical, made rigorous understanding of what perspective means has to do with the act or the transformation of projection. Okay. So why is it called projective geometry? The answer to this question is the previous notion of being in perspective can be described in terms of the operation of projection. But we're going to have to define what we mean when we talk about projection. So you're familiar with at least some type of projection. So we want to talk about projections here. Okay. Okay. So, note, R3 contains many planes, not necessarily through the origin. Right. So then each plane P not passing through the origin can be regarded as a perspective view of the projective plane RP2 right, a view that contains all but one line of RP2. So you might already be thinking, what line would that be? So this is important enough that I'm going to box this and put little stars next to it, because this is what ties together our notion of perspective that we started this chapter with, and what we've been doing here developing RP2 and how this is related at all, to these things. Okay. All right. And so, how does this work? So each point P of my plane not passing through the origin, script P. So each point P of script P corresponds to a line of sight. You can think of through the origin. And thus, a point of RP2. Well, this kind of does it already, right? So any point of my plane script P, so every point of this plane, point in the Euclidean sense, right? Every point P of my plane script P that doesn't pass through the origin corresponds to a line of sight through the origin. That line, as it passes through the origin, it is a line through the origin in R3, and thus it is a point of RP2. And so we have matched a point in our plane to a point in RP2, and every single point in our plane is matched up in this way to a point of RP2. Now, when you have a transformation like this, right, you're matching up point by point. So every point of the plane that we started with is matched up to a real projective point, but does it miss anything, right? Is that an onto transformation, right, in some way? So does it miss any points of RP2? It does. It does miss some. It misses exactly a line's worth of points, right? So the only lines, note that the only lines through the origin that do not meet script P are those parallel to script P. Okay. And these make up the line at infinity So these make up the line at infinity or horizon of my plane script P. So recall our example of the plane z equals -1. Okay. And so in this way, we can think about projecting from our plane script P to RP2. Similarly, I can actually think about projecting from one plane onto another, where neither plane passes through the origin. And so we're gonna talk about that next time, because this is going to lead to some very nice things. So this is going to lead to like one of the most powerful tools to help us understand projective geometry, which is we're going to get fractional linear transformations out of this, and using these we are going to come to understand the most fundamental quantities about projective geometry. But I'm out of time for now. So anyway, we'll start there on Wednesday. I have office hours today, as I mentioned in the announcement, so because your homework is due tonight at midnight. So I have office hours today if you have any lingering questions about your homework. So I will be here 3 to 4 is when the office hours are. So I will send a link like a little bit before 3. I have office hours right before that too for another class. So right around 3, maybe if it's like 3:01, 3:02, don't freak out too bad. But yeah, so I will send a link when those are ready. So have your questions about the homework ready for then. Anyway, I will see you Wednesday.